So we're going to talk about the Jahn-Teller theorem. And so this is maybe something that you learned about in an introductory inorganic chemistry class. Hopefully here we'll clear up some things and go into a little bit more depth than you have before. This theorem states that any nonlinear molecule within a degenerate electronic state will distort as to lower its symmetry and remove that degeneracy. Okay, so basically the lower symmetry state when you have degeneracy will, in a higher symmetry state, will always be more stable in the ground state, okay? And why is this? First of all, let's just clarify this nonlinear part. If you have a linear molecule and you do a distortion, it's still linear, right? And so that's why, at least when there's two atoms, this is gonna have to be a non-linear molecule. All right, so this theorem just says that a distortion will happen. You will get a distortion to lower symmetry, but it doesn't tell you how. And a lot of times there's multiple different ways you can convert one high symmetry structure into a lower symmetry structure. So it doesn't make a prediction about how, okay? When you lift this degeneracy, you go to that lower symmetry, the electrons will occupy lower energy orbitals. And this is going to give an overall lower state, especially when you're talking about the ground state of a molecule. And when you have these degeneracies in the electronic states, another way of thinking about it, about this theorem, is that those sort of perfect higher symmetry geometries actually can't exist, okay? Because the distorted molecule is energetically preferred. But we kind of use this, hey, we're going to do this distortion from this higher state to sort of explain how these lower symmetry states end up existing, okay? And so, just a general point here that's related is describing complexes as octahedral or tetrahedral or square planar. That's oftentimes an approximation of their true structures. Sometimes it's a very good approximation, and you can run through all the group theory analysis, run through all the spectroscopy, and see how it all ties together, and it'll make pretty good predictions. But usually there's some slight, for certain cases, there's some slight distortions that occur, okay? So let's go back to our octahedral geometry. We know that crystal field theory tells us the d orbitals are going to split into 3 triply degenerate T2Gs and 2 doubly degenerate EGs that are higher in energy. And so we can look at all the different electronic configurations that exist. And if we have degeneracy in those electronic configurations, the Jahn-Teller theorem predicts that there will be a distortion down from octahedral symmetry into a lower symmetry. If there's no degeneracy, there won't be distortion, and the ground state of the molecule should be octahedral. And so what do I mean by electronic distortion? Here's an example. Let's say you have D1 configuration. You're going to put that electron in the T2G. Okay, it's not going to go in the EG because that's a higher excited state. But you could write that electron could be spin up in any of these different orbitals, right? Any of the triply degenerate orbital. So there's triple degeneracy of this D1 configuration. This tells you, because there's degeneracy in the electronic configuration, that there will be Jahn-Teller distortion, okay? D2, similarly, is also going to be triply degenerate. You could have 2 in the first 2 orbitals, 1 on the end orbitals, or 1 each on the last orbital. So that's also triply degenerate. Those are, clearly the same energy states, okay? And so you can walk through this and figure out, which states, and you should be able to come up with this just by drawing a simple electron configuration diagram. But, pretty obviously, if you have D10, there's not going to be any degeneracy there. There's 10 electrons in all the 5 d orbitals, so 6 in the T2Gs and 4 electrons in the EGs. There's no other way to put that, so that's non-degenerate, okay, or singly degenerate. And some of these other cases are also non-degenerate, like D8. That means you have 6 electrons, your T2Gs are filled, and you have 2 of the same spin in the EGs. So there's no other way to put those without changing the spin, which then that's changing the energetics of the system. Okay, that's not a ground state. If you have one spin up, one spin down, it's not maximizing spin according to Hund's rule, so that's not a ground state. Some of these will be doubly degenerate, D4 high spin, D7 low spin, D9. Those tend to have unpaired electrons in the EGs, okay? And so that's how this all works. Now, the ones that are triply degenerate, these are going to have weak Jahn-Teller distortion. There's going to be Jahn-Teller distortion. You're going to go away from octahedral. You're going to go to a lower symmetry, but it's going to be a weak effect. It's going to distort a little bit. The doubly degenerate ones are going to have strong Jahn-Teller distortions. And if you're not degenerate, it's going to be octahedral, no Jahn-Teller distortion. Why do you have strong Jahn-Teller distortion for the EG orbitals and weak Jahn-Teller distortion for the TTG orbitals? That is because these ones, these doubly degenerate, again, these have to do with unpaired electrons in the EG orbitals. Those are the higher energy states, right? Those were the ones that were pointing more directly at the ligands. And so if you can lower the symmetry to avoid this electron-electron repulsion that's happening on these high-lying EG orbitals, that's really going to be a good thing in terms of stabilizing the structure. So that's why you have a strong Jahn-Teller distortion for these cases. The T2Gs, right, those aren't as strongly interacting with the ligands. And so, yes, there is going to be a preference to going to a lower symmetry, but it's not going to be as strong. So that's why it's going to be a weaker effect, okay? And so for octahedral Jahn-Teller distortions, you can, one way to distort, okay, and a very common way of distortion that ends up occurring is to distort to D4H symmetry. And so that will occur if you take axial ligands and you elongate them or you compress them. And then you'll have, you'll lower down into symmetry to D4H. You can't predict using Jahn-Teller theorem whether or not you're going to get elongation or compression, okay? So an example of a complex, very common complex with strong Jahn-Teller distortion is a D9. Again, D9 has a double degenerate EG electron configuration, so that's why it gives rise to strong electron configuration. It's this copper 2 hexaaqua complex. And you can see you have actually, in this case, elongation. And so the axial ligands are much longer than the equatorial ligands, okay? So we can think about the molecular orbital diagram, or sort of take this from crystal field theory. They're similar. Crystal field theory is just looking at part of the molecular orbital diagram and not including bonding. It's just looking at electron-electron repulsions. We can look at these, right? And so we can ask, all right, use the correlation table, octahedral to D4H. How are the EGs going to split? How are the T2Gs going to split? EG is going to split into an A1G and a B1G. T2Gs are going to split into an EG and a B2G. And so how do we figure out what d orbitals these correspond to? That is how, when we would go to the D4H character table, right? And we could look at the different functions for the d orbitals, right? And find out, oh, okay, XZ and YZ, that's going to be EG in D4H, and the XY is going to be B2G, for example. So that's where we can get all of these. And then we can draw a diagram like this, where here's thinking about compression, okay? And so you can think about, all right, we know T2G from the correlation table splits into EG, and we know from the character table of D4H what those orbitals are. So are the XZ and the YZ going to go up or down in energy as we compress the axial ligands? Well, these have electron density in the Z plane, so they're pointed upwards. So if you bring a ligand closer to it, that's going to increase the electron-electron repulsion and cause the energy of these two orbitals to go up. And because you have to have, you know, the overall energy not change here, they're going to go up, let's call it a third, right? And so the B2G, the other one that's going to go down, those are going to have to go down by, that orbital, the XY orbital, is going to have to go down by minus two-thirds, right? To balance things out. Very similar line of thinking here for compressing and thinking about the EG orbitals. EG orbitals compressing, the DZ squared is going to go up in energy. DZ squared, of course, has its big lobes pointed in the Z direction. You move those ligands closer to that direction, that's going to cause this orbital rise up in energy by 1/2, and that's going to therefore cause the other orbital that came from this EG, the X squared minus Y squared, to decrease by 1/2. keep everything at the barycenter. Overall, nothing changing in terms of energetics. Elongation is the exact opposite, okay? So now the dz squared goes down because you pulled the ligands further away, still D4H symmetry, but you pulled the ligands further away. And the x squared minus y squared are the ones that are going to go up to compensate for that. And again, the exact opposite here, the ones with a z in their name, dxz, dyz, those are pointing towards ligands, so those are going to go down as the ligands get elongated and go around there, and the xy is going to go up to compensate that. So elongation versus compression, same idea, we just reverse the order in these pairs, okay? What's kind of interesting is you can go to an extreme case of Jahn-Teller distortion where you can actually say, what happens if I make it infinitely long, elongated, right? And look what will happen. Here was elongation, you had an x squared minus y squared, you have a dz squared there. And essentially what you're gonna make is you're gonna make the square planar diagram, right? If you rip off, you elongate those octahedral axial ligands so much so that they're completely gone, you're just left with a 4-coordinate square planar system. And so this is actually a way to derive from octahedral the ML4 D4H symmetry for square planar. So that's pretty interesting that that all works out there. And you can see, because of that, this is rising up about the same as this is rising up. So this gap between the B2G and the B1G is pretty similar to delta O. So that can be kind of useful. So yeah, the ligands are removed and you get square planar. This is basically a Walsh diagram is what we made. We made a Walsh diagram between ML6 octahedral and ML4 D4H, right? We have two sides of the diagram, two different structures, and we're asking what happens to the energy of the different orbitals. And this is the same result that is predicted directly from square planar from CFT. If you go back and look at those CFT energetics, right? We could do that. And those CFT energetics are right here. So if we look at square planar, right, we have that x squared minus y squared being really high in energy. Again, it's the same pattern that we just derived from octahedral.